Joining my talk. Good morning, everyone. So I'm going to expand a bit on reduced precision that Corey and Dennis foreshadowed in the last module. And specifically, I'm going to focus on the A100 architecture's use of reduced and mixed precision that we use on data GPU. And even more specifically, I'll only be covering for deep learning frameworks, PyTorch and TensorFlow, focusing mostly on TensorFlow. Now, the use of reduced precision relative to 64-bit double precision floating point values has long been a way to accelerate traditional simulation codes on CPUs, especially with the reemergence of vector architectures. Sorry, actually, I should make this big. Everyone see this? I'm going to walk through the README. Let me know, and feel free to interrupt me anytime if you can't see something or have a question. So we've always known, I come from computational astrophysics, and we had a switch in our code to just turn all the major values from double precision to single precision. We often got 2x speed up right out of the box on major CPUs. Big part of this was because we were memory bandwidth bound, and so we're able to move twice as many values across the bus at a time. But also with the reemergence of vector architectures, you can usually compute twice as many values, and add or multiply in a vector register when they're at single precision. So in deep learning and on GPUs in particular, this strategy has kind of been taken to an extreme and has gained a lot of success in the last few years, partly because deep learning models are highly tolerant of such reduced precision, whereas even in simulation codes, just dropping half the bits for your values might be problematic if you have a stiff ODE or something. So GPUs, given they're trying out different things in the last series of architectures, and tensor processing units coming from Google, similarly, and these other ASICs are trying out different ways of fitting as much in as few bits as possible and speeding up your deep learning models for training and inference along that line. So here's a comparison of two IEEE 754 standard floating point single and half precision values, which are codified and supported everywhere. But then there's also TensorFlow 32, which isn't actually a type, we'll get into that later, but which is being used on the Ampere architecture, kind of an intermediate value, and bfloat 16, which actually stands for brain float. I had forgotten that the B in bfloat 16 stands for brain because it comes from Google Brain. And this is only 16 bits as well, but it's allocated in a slightly different way than half precision. Whereas TensorFlow 32 is actually 19 bits, but you can't actually store a TensorFlow. So this talk will discuss what we can do to use TensorFlow and PyTorch to utilize these types of quantities to accelerate training. I encourage everyone who's interested in this topic to check out these tutorials from last year. They're really helpful when I went to draft this talk. Also from last week, NVIDIA gave a talk at the hackathon on the profiling software, which we'll get into in the TensorFlow hands-on. That's not public online yet, but I'll talk with the organizer to see if we can post it and share it. So a big reason why we are interested in reduced precision quantities and calculations is because in the latest series of architectures from NVIDIA, they have something that you've probably heard a lot about, but might not know the details of, which are tensor cores. In fact, in the A100, you have 432 tensor cores, which is actually a drop from the 2 architectures ago, V100 from Volta architecture. You can see here the ratio is actually 8:1 CUDA to tensor core, and in the A100, it's 16:1. But these tensor cores, we'll take a step back. What they can do is they can do 4x4 matrix multiplications in these reduced precision formats, matrix multiplication and accumulation. Whereas your standard CUDA core is just going to do a single scalar operation. So there's a possibility for, I think the quoted number is 8x or 16x speed up if you go, on the theoretical basis alone. So the tensor cores, there's fewer of them on an A100 than a B100, but they're much more capable now, and this is where I became actually interested in using it. I've done some stuff with the V100 floating point 16, but only manually and by hand, and not throughout my entire deep learning codes. But on the A100, it's much more usable because principally you're able to take floating point 32 inputs and actually compute this product and accumulation on the tensor core. You're not just limited to half precision here. In fact, you can do double precision. I haven't tried that, but that's possible too. And there are some intrinsics in the lower libraries for doing bfloat 16 operations, but that's not quite supported yet in TensorFlow. Also, here's just a fun shot of what a streaming multiprocessor looks like on the Ampere architecture. So you can see the 16:1 ratio and inside here of the CUDA cores to a big, I don't know if this is to scale, but it's the big tensor core. Whereas on a V100, it's 8:1. But there are a lot of differences, as I just explained above, how these tensor cores work. So how do they work? The big difference on the A100 is the addition of this TensorFlow 32 mode, which I just brought up. So the idea is now you can use floating point 32 single precision input matrices. What happens automatically is that they get converted to this TF32 representation internally. It's not stored in memory anywhere, but these 19-bit operands are multiplied, and they're summed onto this running accumulation in floating point full precision 32. So that way it can be invisible to the user, where you're just be able to use your normal single precision deep learning code or even simulation code and perform, block matrix multiply at full single precision, but underneath it's actually using this TF32 mode. Compare that to what was possible on V100s from the last architecture, what still is possible now in the A100s, but where you had to use a half precision multiply and then accumulate into the single precision value. So what TF32 operates with those 19 bits is it combines the range of the single precision format, which is 8 bits in the exponent, with the short precision of half precision by only having 10 bits. So it's kind of a compromise between the two codified standardized formats. You can disable this TF32 at kind of the system level, although it can be somewhat tricky. We can go into details later, but it's theoretically as simple as just exporting an environment variable or setting an environment variable before you launch any application on the GPU. And we'll explore that in the hands-on. So automatic mixed precision, theoretically you could use these quantities, you could use these tensor cores and hand code everything yourself in your deep learning model, and if you're writing it in low-level libraries as well, you could just directly use these tensor cores as they're exposed. But in order to make them actually useful to the average deep learning practitioner, researcher, engineer, NVIDIA started publishing techniques on mixed precision back in 2017, started releasing software around then. Principally, I really recommend this paper if you're interested in the topic, Misikevicius from iClear 2018. Then shortly after that, they released Apex, which actually I didn't know this until I was writing this, stands for a PyTorch extension library, which principally had a automatic mixed precision or AMP module was released, and that was the main way of using mixed precision simply in PyTorch with minimal modifications for several years, until just last year a lot of the core got moved upstream into PyTorch and you shouldn't use Apex anymore. So there's some instructions on how you just use the built-in AMP module in PyTorch to achieve the same results now. And in 2019, these techniques were also ported to TensorFlow and made it much easier to actually use half precision where you can engage the tensor cores and get better performance through TensorFlow codes. And now NVIDIA AMP is it's not actually a library as far as I understand, but it's just a collection of these lower level library calls that target the tensor cores and the associated techniques in deep learning model training in order to get full accuracy and high performance. So here's a nice little diagram of some marketing diagram of how they visualize that. But AMP, you can't just go and change everything to half precision or bfloat 16. The mixed part in the name tells you that certain things are still kept in standard single precision values. So this is what AMP makes easy, is it picks out what is worthwhile to convert to lower precision, and 2 is safe to do so. So certain things in your standard neural networks, certain operations are clearly computationally intensive and performance critical, like dense layers with matrix multiplications, convolutional layers. And these can safely be computed in lower precision as that tensor core multiply in FP16 and accumulate in a higher precision value. The higher precision format is one that's amenable to these operations. You can also do lots of activation functions such as ReLU, and those are pretty safe to perform at half precision and can be expensive depending on your activation. But other operations should always be left in full single precision, because either they wouldn't benefit from, they wouldn't be computed any faster in lower precision, or more critically, if they didn't have the requisite range or precision, you have really bad effects on your training. Functions like computing an exponential, computing a loss function, having some complicated optimizer beyond stochastic gradient descent like Atom, you want to do that in full single precision. Batch norm, softmax, which uses exponential functions. These are often quoted as leave those in float 32. And so what AMP does is, you'll see in these frameworks, is you don't have to go through your code and change the D type of all these layers to whatever the common sense practice is for, should I convert it to half precision, B float 16 or something like that. You won't hard code it, but rather you just use a single line, and AMP is going to do it for you. You really need a GPU though from Volta on in order to actually benefit from using AMP. But other GPUs, I will say, as vast as Tesla, Kepler, can also benefit from not doing everything in float 32, even if they can't use tensor cores. That's because just like in simulation codes, you can decrease your memory and bandwidth usage when you get rid of half the bits. So what mixed precision does, in addition to just picking which layers can be computed in float 16, is it actually keeps all your trainable weights in these master copies in single precision. And then during training, it's going to downcast the safe ones or the performant ones to float 16 or B float 16, do the computations there, and then going to return to accumulate them on the master copy weights at full single precision. They'll become clear in the hands-on and in this next section. Any questions so far? Check chat. I'm not sure about, I think Fugaku's exascale claims, Alfred, are using half precision or some machine learning data type on their ARM64. Someone else can weigh in on that in the chat. Yeah, it depends on what you count as a flop. So in addition to just casting things back and forth from single to half precision, you also, in some cases, need to do one more step, which is known as loss scaling. And deep learning practitioners certainly have heard of a problem that's been around for a long time, which is that of vanishing gradients. And that is when you go very deep in a neural network, or have a very wide neural network even, your gradients can get very, very small. And so people have developed entire architectures trying to ameliorate this problem, including the ResNet architecture with its skip connections, to avoid these vanishing gradients, because if your gradients go to 0, your network's not going to train or learn anything. And so things are certainly exacerbated when you go to, let's say, float 16, where your range and precision are much smaller. In fact, look how large the smallest normalized positive value for float 16 is compared to single precision. But what in that paper, that original paper from the video, what they realized is that if you do, let's say, a histogram of activation gradients, here's an example, they found that while in certain networks, they're very small and they suffer from this vanishing gradient problem, there's a whole area of the floating point 16 representable range that's not being used. This dynamic range is completely unused if you represent these values, which are cast, from single precision to half precision, and this is where they would end up lying in that range. And so what they realized is that you can scale the loss by just a constant factor, several orders of magnitude, moving the histogram up into the representable and normalized range. And that will prevent these values from being clipped to zero in the reduced precision representation. So this is an essential technique, especially for specifically activation gradients, as I highlight here, whereas weight gradients and just plain activations aren't usually going to suffer from these small values. So it's an essential technique in some deep networks they found. So if you start using mixed precision, be sure to check and find that it really affects your training. Be sure to check your, just bin your activations in TensorBoard and see if you're doing the loss scaling correctly. So here's a flowchart of basically how mixed precision works without loss scaling. So if you start from your master copy of your weights, it's kind of confusing. It is a cycle, but let's say this is where you start, and on the forward pass here, you do a bunch of operations in floating point 16, your convolutional layers, to get your activations, and at the end you get the loss, which is actually stored in floating point 32, but then gets downcasted when you do your back propagation to half precision to compute the gradients there, because that's very expensive, as Corey's example showed, the back prop step. And then you compute all the gradients in this reduced precision quickly, but then you store them accumulate them in half precision, in single precision, and then you pass that back to the optimizer. And that's how it looks without loss scaling. Pretty simple, just casting operations, as I indicated. With loss scaling, it's also simple, but there's just a few intermediate steps of where you apply this alpha factor that might be changing between iterations to scale that histogram. So starting in from here, downcast to half precision on your forward pass, get your loss, which I said is stored in half precision. But now you scale it, just multiply by alpha, which gives you, by the chain rule, the similar scales of gradients by that same alpha factor. So you compute them in half precision, you accumulate them in single precision, but then you have to remove the scaling when you go to actually apply the gradients and update your trainable weights, because otherwise you're going to, you have some optimal step size, and if you multiply that by alpha, your step's much larger if it's greater than 1. So we have to just remove this scaling, and it's just a neat trick to get around a finite precision artifact that would have normally occurred here. Any questions on loss scaling? Chat. Nothing? Okay, so that's it. That's all there really is to mixed precision. It can be more complicated if you use something like B floats, but unfortunately, as I said, they're not supported on GPUs right now, although I'm sure they're coming. But you can even play around with B float 16 mixed precision on Google Compute Engine on the cloud if you're using their TPUs, which it's supported since generation 1 of their TPUs. So now we're going to go into a hands-on example where we're looking at how to do this in TensorFlow. This is where we're going to do some profiling, and we're going to play with loss scaling. We're going to dig into more of the numbers from Corey's example of precisely how much tensor cores affect things. The PyTorch example's just like a one paragraph thing, because the technique's not very different, because they all use these same techniques. Like I said, that's part of the AMP collection. And if people want to, use PyTorch, I recommend checking out the NERSC SC20 tutorial, which is a PyTorch example. Okay. So, okay, everyone can see my terminal. I hope it's large enough. You also yell at me if it's small. So we're going to do, you can follow along now. As Corey mentioned, you can just run it later as well on your own and ask questions in the Slack. I'll be as responsive as I can. So I'm going to try to run most of these with you, but all the results should also be in the notebook. And I can also just share like the profiling results, which is about 1 gigabyte for all the examples I have. If you don't want to run it yourself, but just want to look at the results. So we're going to use the GAN example from the previous TensorFlow profiling module. But we're going to use a slightly different container, because we found that container image actually has issues with disabling tfloat 32. So I'm on a Theta GPU service node. So I'm just going to grab an allocation. Quick, I could just grab the reservation, but it shouldn't be too bad. I'll just show you where I am. Okay, so I've got some other profiling results here that's not in the repository. And also, if you're trying to follow along, be sure to git pull the latest. As late as this morning, I was pushing some updates. Here's train GAN optimized that Corey wrote and that I took. Okay, so now I have a single GPU on Theta GPU. So I'll run this singularity container. This was built from NVIDIA's NVIDIA GPU cloud containers that they distribute every month, more or less. So here's their optimized one for TensorFlow, but I'll stress that these mixed precision abilities and benefits for NVIDIA GPUs are upstream just on TensorFlow GitHub as well, but this is convenient. But we did find that this one is this month's release is much different than the one in February, as was mentioned in the previous module. Okay, so we're going to now explore custom loss scaling. So Corey mentioned that activating mixed precision in his code was as simple as one line in TensorFlow's Keras API. That picture was not quite accurate because of the loss scaling issue that I brought up. Namely, we don't know if even though it performed faster by 40,000 or so images a second just by activating mixed precision through this line right here, we don't know how it really affected the training or the accuracy of the train classifier or the generator. So we should actually add the loss scaling during training to do everything quite correctly to prevent from clipping or vanishing gradients. So what this code does is already implemented. First, some quality of life improvements. At the top, you can see it's added these two switches, which one turns on the mixed float 16, float 32 precision here, and this one turns on the loss scaling. Additionally, it also starts logging the losses to the tensor boards. You can visualize them, and that's about it. So let's look at what the loss scaling. So here's the training loop that was discussed in detail last time. So you can see the generator step being the first half of a single iteration, where you do the forward pass here and get the loss. So now, by default, we're going to use the optimizer, which is in Keras, the optimizer object, which is now wrapped in this TF Keras mixed precision loss scale optimizer object around what was previously there, your atom and your RMS prop. This is basically just a high-level wrapper about keeping track of what that scale factor is, because as I mentioned, it can change a lot throughout training. You don't want to use necessarily the same scale factor at the beginning of training as you do in the end. So this step right here just scales it by whatever that factor is, just multiplies by alpha. And afterwards, during the backward pass here, you end up with scaled gradients. This is the same call as before, but instead of using just the plain loss, it's going to take in the scaled loss and return the scaled gradients. And finally, we just use that same wrapped optimizer, and we get the unscaled gradients because to do the actual application update of the trainable weights. So these are all summarized right here. So to compare how this affects training, I've changed the number of epochs to 100 from whatever the default was. So we'll run it for the entirety of this amount. So first we'll run it without mixed precision, and so the loss scale doesn't matter because we're doing everything in single precision. Make sure that there's no pre-existing log directory here, so RM everything ran previous experiments. But other than that, as I indicate right here, we're just going to run it straight, no profiling or anything, since we're only interested in how mixed precision affects accuracy. So this will take a minute. While that's running, we don't want to give away the results. It will bring up that, so the reason we have to do these manual loss scaling steps is anytime you have a custom training loop, which as researchers is often the case. But if you're just using kind of a standard network and a standard training loop, Keris's high-level API, you might know, offers just a fit operation. In that case, you don't have to do any of these steps, and that the loss scaling is just going to happen in the background when you do use that one line. So it can be as simple as a one-line change to effectively use mixed precision without hopefully affecting your training accuracy. Another detail is that I don't think at one point in Apex and within the original version of the TensorFlow automatic mixed precision API, you were able to mess around with the scale factor, specify it yourself. But now I think it's pretty hidden, and the technique is pretty much the same through the two, and through both PyTorch and TensorFlow and MXNet and Paddle, which is another deep learning framework that AMP is available on. And basically, the scale factor starts extremely large because there's really no harm and very little risk in having gradients overflow in these cases and exceed the half precision representable range. So it can start as large as 2 to the 24, which is the largest representable integer in float 32, or even 65,000. And it's going to multiply all of the loss directly by that. So the code's going to automatically check if there's any overflows. But if there aren't any, then it will you keep increasing the scale until it hits an overflow. And this is after some requisite number of steps that I believe is 2,000 in the code, 2,000 iterations. Otherwise, it's going to decrease the scale by 2x and check if there's another overflow. If not, then it'll use that value instead. So this is running in single precision. And let's take note of the images a second. This, I believe, is pretty close to what it should be, exactly the same to what the single precision XLA results were from the TensorFlow profiling case, because the code hasn't really changed since that with all the switches deactivated. So about 98,000 images a second on a single GPU. I'll go ahead and it's almost done. So I'll turn on mixed precision and I'll turn on loss scaling. Rerun that. That's going to take another minute. So while that's running, I'll start getting ready to connect to the tensor board to visualize these results. Again, don't want to spoil the results. So you can follow these instructions. I think a couple speakers have already covered what it takes to tunnel into a Theta GPU compute node. Or of course, you can copy, once this is done, copy the logs directory to your local device and just visualize it through TensorBoard there without any SSH tunneling. But I'll do it through SSH tunneling here on my local machine. Luckily, my Z shell saves all these commands, so I don't have to memorize them myself. But let me increase the size of this tab. So I just pick a port number. The default for Jupyter notebooks is 8888. So I think in the Theta GPU documentation, we just say pick one more than that. And then tunnel to the fixed KNL login node. I like number 5. I just use it because so we always land on the same node. Whereas if you just use theta.alcf.anl.gov, you could end up on any one of the 6 or so login nodes. Okay, so that's open there, and then I need to make another hop to the GPU. Oh, and this is something I always forget, which is to take note of which Theta GPU compute node you're on when you're first get the allocation. So I can check that with I like qstat-f and then rep my name. So I'm on, okay, I am on Theta GPU 5. I found that every time I ask for a single GPU, it puts me on this node. I think that might be the only node running that queue. Someone else can tell me if I'm right or wrong. Okay, so now the tunnel's open, so I should be able to direct my browser to localhost colon port number. This tab open, but in case you don't believe me. Oh, it's not running yet. I have to wait. The tunnel's open, but TensorBoard's not running. We have one more run to complete. To be clear, again, marking, so we're now doing loss scaling and half precision or mixed precision. So this is 115,000 images a second. I think you get much higher, or a bit higher, if you're on a full node as opposed to the single node allocation, maybe because you're not sharing the CPU. But regardless, it's faster here. Let's run it one more time. Turn off loss scaling to see if this truly matters. So the way the switch is implemented in the code, normally it would just dump out each time you train the code. It would put out the loss curves and some named by the start time or something. But this just adds a suffix to tell you if you're using a scaled loss and mixed precision, just to make it easier to interpret. Another thing we'll dig into more after this section, but you can see now, is that the initial iterations take a long time and are much slower than the later iterations. Those familiar with TensorFlow are familiar with this, especially when you use XLA, because during these initial steps, this is when your kernels get compiled by XLA, which takes quite some time. They're JITted. And also the calls to cuDNN from TensorFlow often run heuristic algorithms to be like, what's the best convolutional algorithm? What's going to be the fastest on this architecture with these shapes? So that takes, I think for this one, took the first 10 iterations. Obviously, if you're running hundreds of thousands of iterations, those startup costs aren't going to be significant, but they can be if you're just running a short network like we are here for a short amount of time. Any questions? Okay, halfway done with this training, then we'll look at TensorBoard. Okay, this is completed. So TensorBoard's run as before. This time we have the metrics that we decided to dump into the profiles are now going to be present in there. It's not just going to be performance profiling. Okay, so here are comparison loss curves. There's a bunch on here because we have both discriminator and generator loss curves. So the dark blue and the orange are single precision, kind of your reference values for what normal training would be. And you can see the green line and the pink line closely agree, loss curves closely agree, especially at the end with the loss curves of single precision. So this is with loss scaling. Whereas the blue line, sorry, the light blue line is with loss scaling for the generator. Ultimately, this isn't the best example to run. We just basically are looking here for that mixed precision training with or without loss scaling didn't cause the gradient of one of the discriminator, either the discriminator or the generator to basically explode and diverge. And I've looked at the results of the generator, the images that are produced when you run it with loss scaling, and they agree with the single precision one as well. I encourage you to check that out as well. You can refer back to, I wonder if there's a link to the original GAN example that Corey wrote, where it tells you how to get the generated images out of it, like he showed in the previous profile. But you can check all three of them, and they all produce legible MNIST digits. So this, unfortunately, wasn't a very satisfying example to use to demonstrate the importance of loss scaling, but it's actually what NVIDIA found is that many networks work out of the box for mixed precision training, and loss scaling is not necessary. But it's good whenever you're implementing this, since it's only a few lines extra on top of the one line it takes to enable AMP to add loss scaling. Here's an example of big LSTM from that paper where they trained the model perplexity over training iteration, and they compare, like we did right here, the reference single precision training loss curve, the mixed precision one with no loss scaling, or loss scaling of 1, and loss scaling, which they actually use a fixed one, 128, and it is essential in networks such as LSTMs, which are already vulnerable to vanishing gradients due to the way recurrent neural networks work to vanishing gradients, and it becomes way worse once you switch to mixed precision. So here's actually with a different seed. You can see that ultimately they end up at the same place, and none of the models suffer from the exploding loss curve. Sorry for my dog. Okay, so that's encouraging. We've checked out the accuracy and concluded that it's fine. Mixed precision training is safe, and we're getting all this extra throughput, and we don't have to worry about the accuracy anymore. But now let's dig into how much the tensor cores are actually vital on the new Ampere architecture from last year. So back again to this compute node. We're only on a single GPU node. And so now we're going to play around with this environment variable that disables TFloat32 operations on the tensor cores. So first, this is going to have no effect if you're already in mixed precision training, because as mentioned before, you don't need TFloat32 when your operands are half precision float 16. So let's keep everything in single precision just through vanilla network. Now we're going to run typo here. Oh, I'm on the wrong. Feel that the reason it was actually a bit slower than the 130 or 140,000 images a second was actually because I left a future change in there. Always work with a clean Git directory. Let's run that again. So I'll note, and I put this in the walkthrough, is that you see right here that actually the TensorFlow logging actually tells you that TF32 is going to be used for the matrix multiplication. And I confirmed with NVIDIA that this, I mean, we'll see in a second definitively that the tensor cores are not utilized. So here it is, that we're only getting 60,000 images a second. Compare that to 100,000 we're getting at single precision with the tensor cores being utilized. Now, it's not quite the factors that are given in marketing from NVIDIA, but it's pretty big, especially for a small, not very demanding network like this. So there's no reason you should really ever use this option unless you're debugging things and you want to make sure that the tensor cores are not actually giving you the wrong answer, or somehow messing up your algorithm. Okay, we don't need to run this for a full 100 cycles. So the throughput's dropped by 33%. But let's say, okay, that's a pretty clear indication that the tensor cores were being utilized in the original network with TF32 enabled, but it's still not direct evidence. Unfortunately, if you go to NVIDIA SMI, let's open up a new window here. You can watch, NVIDIA SMI is not so useful on the way it's enabled right now on the single GPU nodes. I probably should grab a full node. But you can see here that you can see usually get the percentage of the utilization of the GPU, but it's not going to break down if you're using the tensor cores at 70% utilization or something like that. It's just going to give you a very coarse figure. So there's no way to use this tool really to directly check if you're using tensor cores. In Insight Pro systems, it's also not that easy as well, as far as I understand. So I'm going to show you how to use briefly DLProf, which is a profiling tool built on top of Insight systems and on top of Insight Compute, designed specifically for deep learning frameworks, and it can work with PyTorch, TensorFlow, I believe a few others, but it's pretty new. You can ask Max about that, or you can direct you to other NVIDIA people for more details. And like I said, I'll hopefully get the slides from last week's presentation on it in video to share. But we can use this to actually see the tensor core utilization directly. So DLProf is theoretically as simple as just take DLProf, and it's already built into these NVIDIA NGC containers, and just prepend your normal command with DLProf, and here I'll start with mode simple, which just gives you extremely simple statistics about your GPU and tensor core utilization. But you can also dump CSV files with more detailing profiling information, and what we'll explore in a second is you can get these full framework-aware profiles, which actually can correlate your GPU utilization with the actual framework network calls through NVTX markers. But let's just start with this for sanity check to make sure that we're using the tensor cores. So that recall, so now TF32 is enabled again since I'm not using that environment variable. And it's set to just standard single precision training. Let's not run this for 100 epochs. We'll need a few. So the software is pretty new. I believe it's a year or so old, and it's mostly stable. But I'll say I had some trouble when I was writing this. It seg faulted at the conclusion of operations a few times. It was kind of finicky about the flags that are passed to it. So I think if you have any issues, I can give you the contact I have for DLProf to report those issues. But you can see it's actually writing out Insight systems profiles, and on top of that, like I mentioned, it's going to parse those and correlate them with the NVTX markers that are buried in the source code for TensorFlow, even for a simple profile like this, which is only going to give us 3 numbers at the end. It can take a while to finalize, and actually, even for the simple statistics, you'll see here it takes a little bit. And it's if you run this for like several minutes, you do, let's say, 100 epochs, it takes an extremely long time and produces, as it would in Insight systems, a very fat profile database, which is like a gigabyte, for example, even for the small network. Okay, I'm not going to run the other two. It's kind of boring, but I pasted the results here. Oh, here, finally. Okay, not even finished. Okay, there we go. Now, see, even got a segmentation fault here. And this value is quite a bit different than what I measured earlier. Well, you can see that the tensor cores are being utilized for 2.68 seconds, which means it's greater than 0 with the TF32 enabled. So that's a good sign. But relatively, I suppose the wall time is quite a bit different, but the total GPU and tensor core time is about what I expected. So those are the metrics of interest. But when we disable TF32, again, as we see, you actually still use tensor cores because I believe certain operands are still in the code, can be used like this, but the main parts of the layers during the training that would have normally been passed to the tensor cores, because there's, I believe, 3 convolutional layers in the generator alone, and something similar for the discriminator. Those cannot be computed with the tensor cores, so it drops, and the total GPU time goes up. Interestingly, when you run mixed precision, you can see that the tensor core time, somewhere in between the two values, and the wall time actually is the greatest out of all of them. But as I mentioned earlier, when I'm running it, you can see how slow the initial iterations were for training. And it was actually even worse in, you can try this out for yourself, with mixed precision. That's because, of course, there's a lot of heuristics going on to test the safety and the efficacy of using mixed precision for the various layers in whatever network you give to AMP. So even though the wall time is high, that's because the initial iterations are so much greater than even XLA costs for TF32. But we could see, I mean, the values we got for the images per second was by far the greatest when you use mixed precision. Just to verify that, we'll see if we can cover the 140,000 that we got. Now that I won't run the full thing. So let's dig into this. Let's see, what the actual per iteration time is going to be after the startup costs. So that we're going to turn to the full profiling, which doesn't require too much more than your basic simple mode. Runs quite a bit longer. But the one key thing you have to do in TensorFlow 2 versions is that you have to specify what the boundary is between an iteration and the next iteration. Because it's an eager operation, there's no way for DLprop to, as there was in TensorFlow 1, to demarcate what is the end of an iteration just based on the operations that end up in CUDA and end up running on the device. So there's a documentation here, which is pretty simple on how you can determine that for your code. Okay, we got 130,000 or so with mixed precision, which is about right. I'll see it even errors out if the files are still there, so you have to RM or prename them between everything. So you pass that. I did that for this model, and found that this one was called exactly the number of times as there were iterations being run. So I used that, pass that to DLprop to demarcate that. And also I tell it to ignore the initial costs or the initial iterations when computing the statistics for the average runtime or in other ones. So I collected these profiles and I can share them. It would take too long to run on here, I think, and then go through TensorBoard, but they are just visualized through TensorBoard as before, so we can use the same tunnel. So let's actually do that. So here will be TensorBoard here. And like I said, it's it's not a super polished software yet. So like here, I'm getting a ton of errors, and it even always pops up with a server error for me, but I'm able to just click away from it. And this is really amazing for anyone who's used, been using Insight systems or something else, or the other profiling tools that were discussed in the previous section. This gives a lot of information. First of all, you can see the average iteration time over the sample iterations, 71 milliseconds, which if you compare them to the similar profiles collected for non-mixed precision, it's almost twice as fast for these iterations. So you can amortize the startup by training for a long time, as we expected. You can directly examine the tensor core efficiency. Sorry, this is very small. The tensor core efficiency, which is 45%, which isn't great. And if you want to dig into that and like why it's not higher, you can actually go into the lists of GPU operations and kernels, see if they're eligible, and sometimes get advice. There are no recommendations this time for what you can change, and determine whether or not they're being used. This is my favorite part, is looking into the iteration summary. It's mad that I zoomed in. Okay, no, it's good. And you can actually, within an epoch, you can determine which one's the final or the first step of the epoch, because these iterations took much longer than the initial step of whatever epoch number this was. Because if you look at the source code, that's when the data set is shuffled. And it takes almost as long as an entire trading step on its own. And you can determine a lot of cool things from this and see the breakdown by the operations that aren't using tensor cores and how long they take, and versus the operations that are using tensor cores and how long they take. And you can actually even recollect this profile over using a different marker between iterations if you wanted to. So this takes some playing around with to really utilize it for its full potential, and it's really dependent on your particular network and job and your network bottlenecks. Let's go back to the previous collected ones. You can click on these, and these are full screenshots. But just to see, when you disable TF32 and you're running in single precision, as you would expect, the tensor core kernel efficiency is 0%, even though the GPU utilization itself goes up higher because the CUDA cores are more utilized, even though because this network is so small that taking those kernels away from the tensor cores, and you can move them to the CUDA cores with no problem. But the average iteration time is twice as much. So you can really see the advantage of mixed precision and TF32 mode right here, and dig into that. So running a little out of time. So for the last kind of exercise, fun thing here, there's a list of pitfalls when it comes to using tensor cores and mixed precision. And one of the most common ones is you have to use certain layer sizes or multiples of layers of a certain factor of layer sizes in order to actually put the op onto a tensor core. That's because you saw I could do those 4x4 matrices in the previous intro, but you actually optimally utilize them when certain dimensions of layers in the networks are factors of 8 or multiples of 8. So LSTM and dense layers should have 8x units, convolutional layers should have 8x filters, and the batch size that you're passing it should be a factor of 8. To see this definitively, we can go into the code we just wrote. You can play around with this. I encourage you to, after this, to make it a bigger network, see how it affects things, change the dimensions of things. But here's a suggested kind of mess up the generator series of changes, where I changed the dense network to not a multiple of the dense layer is not a multiple of 8. Similarly, I basically reduce all of the filters and units counts by 1. So theoretically, there's less work to do, so it should be faster at pumping images through the generator. But in fact, the performance crashes basically. So here's another profile I collected. The tensor core utilization dropped down to 28% from 45 or whatever it was. The average iteration time actually goes up to the highest of all the cases. And if we dig a bit into the iteration timeline, you can actually pick out within a iteration where you can see where the generator is going to. I think I actually changed the way that the iteration boundaries are demarcated. So the sampling interval is a bit higher. So you can see how the generator, which is messed up and suboptimal with its layers, is actually being evaluated and passed through its forward pass and backward pass versus a generator. This is the discriminator, which still has the optimal multiples of 8 unit sizes, etc. So this could be a really powerful tool to debugging when you have complicated networks and there's one part of your network or your overall model that's slowing you down. So with the last few minutes, feel free to interrupt me and ask questions because this is more or less the talk, but I just wanted to show you that I gave you the recipe in PyTorch here for how you would do that. The only difference essentially with the TensorFlow loss scaling is that you have an explicit object for the loss scaler as opposed to being buried inside the optimizer or wrapped around the optimizer. And you have to explicitly update the loss scaling factor by calling this after each iteration or epoch. I encourage everyone to check out that NERSC tutorial and play around with that if you're more interested in PyTorch than this, but I thought it'd be good to build on the TensorFlow example from Corey's walkthrough. And here's a link to the recipe for AMP in PyTorch. That's it. Any questions?
Thanks, Kyle. This was useful. So I have a question related to, I was running or trying to follow up along. My question would be, was supposed to use all, I could see like I logged into a node and I had 8 GPUs, right, available.
Yeah.
Was supposed that script to use all 8 or not?
You don't have to. So by default, I believe there's actually Horovod in there. So if you listen to Sam's talk yesterday, you could try this out with distributed data parallel training on all 8 GPUs and mixed precision. That'd be an interesting study. But for this, for all the steps I did, was all 1 GPU. And if you just run the commands I ran, it was just 1 GPU. But what's interesting is
that's what I observed.
And if you run NVIDIA SMI, though, you'll see that it appears that it's going to launch a process on each GPU, but only one of them is going to have a percentage of activity. It's going to have high memory usage. Whenever TensorFlow is going to pin some memory on any GPU it sees. So, which can kind of get annoying in the diagnostic log output because you'll see at the beginning it says GPU device 0, 1, 2, 3, etc. detected, but it's only using 1 in this example. So you can export, and I think I put this in the TensorFlow walkthrough. You can export, CUDA visible devices equals 0 if you only want to run on one of those, or just switch to the single GPU queue.
That was exactly my issue because I wasn't sure. I could see like at the beginning recognizing all 8, and then when I run exactly the NVIDIA SMI, it said only one of them showed activity.
Yeah, it's a pitfall in deciphering the TensorFlow logs is a bit of a magic mystery.
The other thing is that the numbers that I got were quite different than what you got.
Oh yeah.
Yeah, like I got something on the order of 180 something seconds for the wall time.
I mean, if you ran, so the absolute value of the numbers might change depending on what the value of the number of epochs is in the file at the bottom. I didn't really go into detail. I kind of just changed that on the fly. But yeah, if you're running 100, it'll take forever. It's the throughput that matters. That's what I really would focus on, what's reported on the command line or through these tools that I discussed.
Okay. When I use the DLProf, I could notice that's just visually. Like I run before with just Python, the train Python script, and then that seemed to process about 100,000 images per second or something like that. And then when I used the DLProf, it seemed like much fewer images.
We can take this offline. I know we're running out of time.
Sure.
But yeah, there of course is overhead with profiling, but it shouldn't be too bad for this. It still should have like the correct ordering of like mixed precision being the fastest, then TF32 single precision, then no TF32 single precision being the slowest.
Okay.
Yeah,
thanks.
Ping me on Slack if you still have issues.
Yep.
Thanks. Okay,